Hello students, today we will take some topics based upon specific heat capacity of solids and liquid, say for water, and after that we will do numerical based upon specific heat capacity. So first we are taking the specific heat capacity of solids. Again, we will use the law of equipartition of energy to determine the specific heat capacity of solid and water. Consider that solid has n atoms in its sample. So solid has n number of atoms, and each atom can vibrate with respect to its mean position. So it will be oscillating, means the atom, individual atom of that solid will be oscillating with respect to its mean position and can contribute its kinetic energy as follows. The contribution of kinetic energy by a molecule of solid is due to its vibratory motion, means that will be equals to 2 multiplied half kVt, as we have discussed earlier that its contribution of kinetic energy will be corresponding to its potential plus kinetic energy, means the sum of potential and kinetic in terms of its mechanical energy. So 2 times of half kVt corresponding to each type of energy will be multiplied by 2, and thus we receive its total energy contribution as kVt. Similarly, the molecule or the atom of the solid can vibrate in 3 dimensions. So the energy contribution in all 3 dimensions will be equals to 3 kVt, where kVt term is the contribution of kinetic energy in 1 dimension. So in 3 dimensions it will be thrice of kVt. Now for a mole of solid, total number of atoms present in 1 mole of solid is the same as total number of that solid, total number of molecules in that solid. So the term n will be equals to Avogadro number Na, then total energy, that is capital U, will be equals to 3 kVt multiplied Na, which can be rewritten further as 3 RT. Now at constant pressure, for the solid, delta Q is equals to delta U plus P delta V, but the change in the volume of the solid by supplying some energy to it will be negligible. In that case, it can be considered as delta Q equals to delta U, because the term P delta V is 0 for solid. So the specific heat capacity of solid C will be equals to delta Q upon delta T or delta U upon delta T, or it can be rewritten as 3R, which is the specific heat capacity of solid at constant pressure. Now we will discuss the specific heat capacity of water. A molecule of water has 3 atoms, 2 hydrogen atoms and 1 oxygen atom, and each of these atoms has 3 degrees of freedom respectively. So the total energy contribution for water can be written as U equals to 3 multiplied 3 of kBT, where the energy contribution 3 kBT is due to each atom in that water molecule and 3 for the individual molecule. So it will be the completely contribution of energy due to all 3 atoms in all that water sample. Further, it multiplied by Na gives us 9RT. So specific heat capacity of water will be equals to C equals to delta Q by delta T equals to delta U by delta T equals to 9R. Finally, we have a short description that as we go for low temperatures, specific heat of all substances approaches to zero. So their degrees of freedom get frozen as the temperature is reduced up to zero. So according to classical physics, degree of freedom must remain unchanged all times. The behavior of specific heat at low temperature shows that it is inadequate. In that case, vibrational degrees of freedom come into play in some cases. So we are limited to just the calculation of the specific heat capacity of solid, liquid and gaseous molecule, but the ideal conditions may differ. Now we will take an example, a numerical problem based upon specific heat. The question is, a cylinder of fixed capacity 44.8 liters contains helium gas. At a standard temperature and pressure. We have to calculate the amount of heat needed to raise the temperature of gas in the cylinder by 15 degrees centigrade. The solution for the problem: the ideal gas equation is given by PV equals to mu RT, where P is the pressure of gas, V is the volume of that gas sample, mu is the total number of moles in that gas sample, R the gas constant, and the T the temperature. As we know that 1 mole of any gas at standard temperature 273 Kelvin and standard temperature 1 atmospheric pressure occupy a volume of 22.4 liters. So we can consider this thing here: any gas, the 1 mole of any gas at STP, standard temperature and pressure, occupy a volume of 22.4 liters. That is called the molar volume. In the given question, the cylinder contains 2 mole of helium gas because the volume is given 44.8 liters. So according to question, cylinder contains 2 moles of helium gas which is a monatomic gas. So its molar specific heat at constant volume is equals to Cv, that is equals to 3 by 2 R, and the molar specific heat at constant pressure Cp is equals to 5 by 2 R. Since the volume of the cylinder is fixed, so heat required will be determined by only the part Cv, the molar specific heat at constant volume. The volume is constant here. Therefore, heat required will be equals to number of moles multiply the molar specific heat multiply the rise in temperature, which can be simplified further as the number of moles given here 2 multiply the molar specific heat which we are taking at constant volume is 3 by 2 R multiply the rise in temperature which is 15 degrees centigrade, and if it would be in Kelvin, the rise in temperature is 15 Kelvin. So it can be considered as the same increment in terms of degree centigrade or the Kelvin value. Finally, putting the value of constant R, we can write here 3 multiply 8.31 multiply 15, where R is equals to 8.31 joule per mole Kelvin. Finally, it can be written by solving it. The heat required is 374 joule. That's our answer for the problem. So that's all for today.